Yes.
HC bar represents the H field at the far left.
Far left, yeah. H field.
At the left boundary.
Yeah. But it is within the simulation.
Okay.
So this movie has PEC boundary condition on the right and left. They are reflective, right? That's the effect of the PEC boundary condition. And I'll show you.
How did you simulate this?
How do I simulate this?
Yeah.
Using numerical?
Okay, so this is.
Oh yeah. That was your question. Okay, I was maybe some more fundamental question. This is the periodic boundary condition, and it's very similar as before, but actually.
You give an asymmetry source.
I'll stop at some point here. The main difference between the PEC boundary condition and the periodic boundary condition is where the node and antinode is located with respect to the boundary. So here, the node, the maximum of the field is located at the boundary. That's because the periodic boundary condition has the simulation domain repeated infinitely. So the source is not only here but also here, and they are at the same distance from the boundary. And when they come together at the boundary, they interfere constructively, which leads to the node here at the boundary. But if you go back to the previous movie, this is PEC boundary condition. We have an empty node at the boundary because, by the way, this is the E field. I'm drawing E field. So at the boundary, the PEC boundary condition assumes that the E field is 0. So we have antinode at the boundary. Yes.
Wait, so you have a field of 0 at the boundary, so shouldn't that be a node instead of antinode? Because antinode is when the field is maximum.
Sorry, I mixed up the terms. So this is the node, and for the periodic boundary condition we had antinode. Yeah.
So, how, if you wanted to model free space propagation, would you, like on a finite grid, you have the boundary being like 100% absorbing, so that any wave that passes to the boundary does not reflect at all?
Which I'll cover next.
Oh.
So we obviously don't want either of these usually. What we want is the first simulation that I showed today when I started the class. So in this case, waves just go out and disappear. There's no reflection or interaction with the next simulation domain. And this is assumed by using PML. This is the next topic. So PML stands for perfectly masked layer. So these boundary conditions we learned just now do not simulate infinite space, as gentleman said, and by surrounding the simulation domain, surrounding the simulation domain by PML, we can simulate infinite space. So PML was developed by a guy named Berenzer, a French guy, in 1994. And this is actually quite recent. So this is actually almost 30 years after E-script. So the development of the E-script, invention of the E-script actually allowed us to do FDTD simulation. But the needs of PML is quite obvious. We need that kind of observing boundary to simulate infinite space, but it took almost 30 years to develop PML. That shows how non-trivial the development is. So it's one of the major inventions. So there are two properties of PML. A, zero reflection. An interface. With other media. So let's say we have a and a regular media. And this is actual boundary. So we have a. Before that, I should have explained how does the simulation domain look like. So when you have a simulation domain, you have a boundary, right? And you surround this boundary with PML. So behind PML, there are actually either of these boundaries, the PEC boundary or periodic boundary. But anyway, let's say the wave is incoming to the interface between regular medium and PML. property makes there's no reflection. There's no reflection. And the second property is efficient attenuation. Of transmitted. So once the wave hits the PML interface, it doesn't get reflected and all transmitted. But after it gets transmitted, it is very efficiently decays. So it is kind of lossy media. So because this attenuation is so efficient, once it hits the, for example, the PEC boundary after PML, there's almost no waves to get reflected. So after reaching true boundary, almost no waves. So, therefore, there's no wave coming out of PML. That's how PML simulates the heating space.
So, what is a TME boundary represent for?
Which boundary? TME.
True boundary.
True boundary. True boundary. So, yeah. Once you put the PML, this PML interface looks like a boundary, but there's true boundary within the PML. Yes.
Sorry, so are you suggesting that property A is a consequence of property B?
No, they're
Okay.
separate.
Okay.
For example, if you repeat the same medium,
Mm-hmm.
there's no reflection, of course, right?
Okay.
Yeah.
So it's supposed to work for all polarizations and all frequencies?
For all polarization and quite wide frequency. Yeah. So I'll briefly mention one of the caveats of using PML and finish the lecture today. So caveat of PML. PML actually attenuates only propagating waves. Not the evanescent wave. Therefore, you should not put the scatterer close to the PML interface. Close to PML. If you put the scatterer close to PML interface, the near field generated by scatterers can easily penetrate into PML. And and reflected. And the true boundary. So I'll tell you one example that I have experienced. So we were simulating this kind of structure. So this is metal, and we put PML. And we put PML here. And we had a source. And it's a plane wave to this slit. Then some gets transmitted and some gets reflected, right? And you are measuring the transmission through this slit. And I knew about this, so I thought I put PML far enough from the scatter. But what happened was this is a scatter, so the field it generates the near field. So the field, if we draw the field amplitude here, the near field generated here gets extended into PML without any decay, and gets reflected here, and reaches to the slit again. This near field was generated by this propagating wave, and therefore this near field can also generate propagating wave conversely. So the near field generated here. Sorry, actually it was not this case. Sorry. So we actually used a periodic boundary condition here. So this near field actually appeared from the back. Okay. So this near field actually excited additional field at the slit and generated the propagating wave, which was not directly generated by the source, but generated secondly by the near field. Therefore, when we measured the transmission here, transmission exceeded 100%. Okay, and this decay length of the near field is really hard to anticipate or estimate before. So you have to be very careful about this. So if you see the transmission exceeding 100%, maybe this kind of first effect of PML is the cause.
So is there a way to distinguish the fields coming from PML and other sources?
It's really difficult. So one way is to put this special boundary farther and farther away, and see if the transmission changes. Once you reach the point where transmission doesn't change, you can be sure that the field, the boundary is far enough.
So why does near field? Why can near field easily penetrate the PML?
For that, I have to spend 2 hours to explain PML. But the fact that PML attenuates only the propagating wave is the property of PML. So it is specifically designed to absorb propagating wave, not the near field.
Okay. So you mean near field is kind of an evanescent waves?
Yeah.
That's why.
Yeah.
Okay.
So that's the end of today's lecture, and I'll see you guys next time.